Solving a right triangle means determining all of the angles and all of the side lengths of that right triangle. So in this instance, if we're given a right triangle, we're not given much information here, but it's actually enough. We know that this is a right triangle, we know that this angle is a 50-degree angle, and we know the hypotenuse has a length of 21 centimeters. That's all we have to start with. But of course, since this is a triangle, we know that the sum of the three angles must sum up to 180, or another way of saying that is the two non-90-degree angles must sum up to 90. So that means this has to be a 40-degree angle there. So that one's pretty easy to finish that part. And as far as the sides, these two legs right here, in order to find those, what I would need to do is I'd say, okay, well, if this is a 50-degree angle, I know that the ratio of this side to that side needs to be something specific. Specifically, since I'm dealing with the side that's adjacent to my 50-degree angle and the hypotenuse, I know I'm wanting to talk about cosine. So remember SOHCAHTOA. Cosine is the one that says adjacent over hypotenuse. Whatever. Cosine is adjacent over hypotenuse. So that means that the cosine of 50 degrees is the side that's adjacent to it, that's A, over the hypotenuse, which is 21. Alright, well that means I can find A, because I have an equation, and that's the only thing that's unknown here. If I take and multiply both sides by 21, I get 21 times the cosine of 50 is equal to A. Well, that's something I can plug into my calculator. 21 times cosine 50. This gives me a side length of 13.5, I'll call it. 13.5. I can do the same thing for this side over here. Let's call it B for the moment. And it is possible, now that I have this side length, 13.5, and I have the hypotenuse, I could go through the process of using the Pythagorean theorem to find this one. However, I don't think that's the best way of going about this particular problem, because I've done some work to find this answer, and I've rounded it. And if I use that answer to then find another answer, then I'm kind of rounding before I get to the end of a problem. Instead, I would rather look at this and say, okay, is there any way I can use this 50 and talk about the ratio of maybe this side and this side? Well, this 50, well, remember, sine is opposite over hypotenuse. So with this 50, that means the sine of 50 degrees is the length of the opposite side, which I'm calling B here, divided by 21. So without doing any sort of rounding or anything before the end of the problem, I can then say B is equal to 21 times the sine of 50 degrees. Looks very similar to this previous problem, except instead of cosine, I now have sine. So 21 sine of 50 gives me 16.08, 16.1 we'll call it. And I'm doing that without, I'm not rounding until the very end of the problem. It's always a good thing to make sure you don't round until the very end. In general, when we're talking about significant digits, so I kind of didn't care about significant digits here. I just rounded the nearest tenth. But when we're dealing with these right triangles, we're going to use this as a guide for the number of significant digits. If we're talking about having two significant digits, we're going to have that rounded to the nearest degree. So these angle measurements are rounded to the nearest degree. I probably should have had these rounded to two significant digits instead of the 3 that I had there, but we hadn't yet seen this, so I'm not going to go back to it. If we're talking about 3 significant digits, that should be rounded to the nearest tenth of a degree or to the nearest 10 minutes. 4 significant digits should go to the nearest hundredth of a degree or to the nearest minute. It's not 100% accurate. That's more of a kind of guidelines as far as where you should be rounding these things to, if you're trying to keep the appropriate number of significant digits. So this one says assume everything, or get everything accurate to 3 significant digits, and we're going to be rounding. So, oh wait, no, this says if side lengths are given as fractions, assume they're accurate to 3 significant digits. That's the other assumption we're going to be making here. All right, if we want to find C in this particular right triangle, well, I know this side is 71 degrees. I have a 90-degree angle here, so we're dealing with the right triangle. I know the side that's opposite, and I'm looking for the hypotenuse. So if I look at SOHCAHTOA, if I look for one of these that involves an opposite and a hypotenuse, you can see I'm talking about the sine. So that means the sine of 71 degrees must be equal to the opposite side, which is 10, divided by c. Okay, well, solving this equation, I'd like to get rid of the 10, but that c is actually in the denominator, and that's another issue. So I'm actually going to start this by multiplying both sides by c. If I multiply this side by c and this side by c, it gets the c out of the denominator. I get c times the sine of 71 degrees equals 10. All right, now what I'd like to do is divide both sides by the sine of 71 degrees. Those cancel out, and I end up with c is equal to 10 divided by the sine of 71 degrees. So when you're trying to figure out what to do for these, don't try to just memorize what's going to happen. Set up your equation and solve your equation just like I did here. I wonder if that's right. 10 divided by sine of 71. I don't know if I can type. Oh yeah, I can. Cool. I wasn't sure if I could just type in sin for sine. It looks like I can though. So this gives us approximately, we're rounding to 3 significant digits. Oh no, wait, that's a different problem. This is rounded to the nearest degree. This is looks like 1, or you could argue it's 2 significant digits. I'm going to call it 2. It looks like this should be rounded to 2 significant digits, which means I'll call it 11 inches. If I was rounding to 2 significant digits.